All right, we're going to do something called finding the DC bias characteristics of the transistor. Finding the DC bias characteristics. And what we're essentially saying is we're finding IB, IC, and VCE. And these go hand in hand. You're not doing one without the other, so it's kind of a collective. I can put in a kind of a side note VBE, but VBE is going to probably be VBE on, except in one special circumstances that we already talked about. So here's our transistor, or here's our circuit. And we're going to use the same circuit we saw in the previous video. It's not quite the circuit that we did in the lab. There was what was called an emitter resistor in the lab. And that adds a little bit of a complication with regard to the analysis, but we'll put that aside for the moment. So we have a V1, we have a V2, we have an RB, and we have an RC. And our steps, when we're doing DC bias analysis, we check if V1, not VI, V1 is greater than VB on, which again, I look at 0.7 volts, and put a little tilde in there. Or I'm going to rewrite that actually as less than, then the transistor is off. And everything is zero. So it's kind of that straightforward. We just stop. So in that case, stop. And so there's no more work to do. The base current, the collector current is zero. IB equals zero. IC equals zero. VC is not zero. But again, that goes to digital electronics, which we'll do a little bit later in the semester. So step two, if we didn't stop, we go on to step two. We find IB, and we had some discussion of that in the last class using KVL, Kirchhoff's voltage law. And if you go and review that video, we find VB is V1 minus VB on, which is at 0.7 volts, over RB. There's our base current, and that's a valid expression. There's a little bit of error because VB on is not 0.7, but it can be pretty darn close. So our next step is, I'm going to go on to the next page, assume, this isn't really a step, assume the transistor is in forward active. So with that in mind, we had that relationship between the base current and the collector current in the previous video, and we can say IC is then beta IB, a linear relationship. I'm supposed to point that out. And so beta being 100, 150, 200, somewhere in that range, the collector current is going to be 2 orders of magnitude larger than the base current. Then our next step is find VCE. And so I'm going to flip back to the previous page and look at our KVL. So we can do KVL around this loop, and we can put little plus, minus, remembering that this is VCE. I suppose we can label that. That's VBE. We have our base current, IB. And then here is our collector current, IC. With that in mind, we can recognize KVL gives us a relationship between the voltage source V2, voltage across RC and VCE. Namely, we can say VCE, let's start with V2 and then rewrite it. V2 is the voltage across the resistor plus VCE. And this is our unknown. This is what we want to find. So the V2 would be given to us. We know what that voltage source is. And so we can rewrite this as VCE equals V2 minus VRC. Well, the voltage across that RC, that collector resistor, is related to Ohm's law, and we had just found an expression for our collector current. We know what the collector resistor is, so we can write this as V2, a known value, minus IC, a known value, times RC. And there's our VCE. We do have a next step. If VC is less than that saturation voltage that we talked about in the last video, forward active assumption is not valid. And I'm going to rewrite this again. I'm going to actually do greater than. So if VC is greater than that saturation voltage we talked about, it is valid, and we're done. So we can stop. We found IB, we have found IC, we found VCE. IB, IC, and VCE are known. On the other hand, go on to the next page here. The next step is if VCE is less than VCE sat, then the forward active assumption is not valid. In which case, we would say VCE equals VCE sat. But, important, IC is unknown. So we've kind of flipped those two. We now know the collector emitter voltage, or approximate collector emitter voltage. And this is about 0.2 volts. We saw that in the data sheet. I mentioned it in the video. But we don't know the collector current. The base current is still correct. So we still have that equation for the base current. That's a reasonably accurate equation. So the next step, if we want to find IC, is to go look at our KVL equation. And here's that same KVL equation. Nothing's changed. So it doesn't matter. KVL is independent of what region of operation it's in. We can now still say V2 is VRC plus VCE. But we know VC is VCE sat. So now we have VRC is just V2 minus VCE sat, or approximately whatever that source voltage is, minus 0.2 volts. And so with that in mind, we can go find our collector current using Ohm's law. Once we know the voltage across that resistor, we can just say VRC, or IC is VRC over RC. We already had the base current. We had just found the collector emitter voltage to be VC sat, so that's a solved problem. And now we have our collector current. You can actually stop the video here, and I'm going to do an example, a couple examples with this math in just a second in our next video.